So we've talked about intermolecular forces, and we know that as the intermolecular forces go up, our properties of our liquids are going to increase as well. And we're going to in particular look at our boiling points, surface tension, capillary action, and viscosity. So make sure we understand our intermolecular forces. So we know that we have dispersion. We know that everything that has electrons has dispersion forces. We know that this is a temporary dipole, and that these tend to be weak unless your molecule's got a very large molar mass. We know that dispersion is weaker than a dipole-dipole, and this is anything polar. Now, we also know that we have a special case of dipole-dipole called hydrogen bonding. We make sure, even though this has the word bond in it, that we know this is not a bond. This is simply an interaction. This is a type of intermolecular force, and it's stronger than dipole-dipole. And if someplace along the line we have to include ionic being iffy as terms of intermolecular, because it's obviously not molecules, but ionic interaction or ionic bonding is going to be greater than any one of these three. So as our intermolecular forces go up, our boiling point is going to go up, our surface tension is going to go up, strength of our forces when we look at our capillary action are going to go up, and our viscosity is going to go up. We see intermolecular forces in all sorts of interesting places. Geckos actually use dispersion forces, or the dispersion forces, in little pads on their feet to allow them to stick on walls and climb up walls. So let's start with surface tension. Surface tension is a property of a liquid. It results from the fact that liquids want to minimize their surface area. And most of the time when they minimize the surface area, we're going to try to get shapes that are spherical. So spheres have the smallest possible surface area. Now, as long as there's no gravity, but on the other hand, if you go to interesting videos off of the space station, we're still going to try to get spherical shapes, even when we have no gravity. So what do we have when we have surface tension? We have a liquid such that we have an internal portion of the liquid and we have our surface. Our surface molecules are going to behave differently than those on the interior. And because of the cohesive forces, cohesive are the forces making these molecules stick to each other. They are going to have a net pull down, and the surface layer is going to act almost like an elastic skin on the top of this liquid. So how does this work? Well, if we look at the molecules inside the surface, they are being pulled evenly in all directions. But the molecules on the top of the surface are going to have a pull side to side, and then they are going to have a pull down. This net pull down is going to cause a force on the top of these, and surface tension, by the way. Surface tension is actually the force required to flatten out the surface, because this surface is going to have a pull down, it's going to minimize the surface area, and it's going to try to form a spherical shape. So surface tension is the force needed to flatten the surface, and it's going to flatten because it's got this net pull down, and this net pull down forces this surface to have a spherical shape. So what is going to affect our surface tension? Well, the stronger the intermolecular forces, the higher the surface tension will be. Now, this is going to depend on temperature, because if we raise the temperature of the liquid, we're going to increase the kinetic energy of the molecules, and this increased molecular motion and kinetic energy makes it easier for these molecules on the surface to move and stretch, and therefore, raising the temperature is going to reduce the surface tension. All right, what about viscosity? Viscosity is resistance to flow. Now, in order to flow, there has to be some sort of motion or some ability of these molecules in this liquid to move. The higher the intermolecular forces, so as the intermolecular forces go up, the viscosity, this resistance to flow, is also going to go up. And there's actually a pitch experiment, and pitch is the sap out of trees, and one drop in this pitch experiment falls about every 10 years because it is so viscous. meaning it sticks together so well that it has a really strong resistance to flow. So let's look at some molecules and see if we can predict their surface tension or their viscosity, or their resistance to flow. So let's think about this. If we have water, now in order to do this, we have to make sure that we can see our molecules. Because if we have intermolecular forces, we know this is going to be in between two molecules. So if we have two water molecules, we know that this intermolecular force right here, this is our IMF. Our IMF here is going to be a hydrogen bond, and this is going to be strong as far as intermolecular forces are going to go. CH2O. Well, CH2O, we know those H's are not on the oxygen. They are going to be on the carbon, which gives us this shape. If we put two of these molecules together, put another oxygen down here, and look at our intermolecular forces, our intermolecular force right here is going to be a dipole. If we look at methane, methane is perfectly symmetrical, and it's only going to have dispersion. And if we do our sulfur dioxide, which we're going to have to draw the Lewis structure for, we're going to realize that sulfur dioxide is going to be polar. It's polar because it's bent, and it is going to have dipole forces as well. So if we ask the question, which of these is going to have the highest or largest or greatest surface tension, it is going to be water. Why? Because it has hydrogen bonding. It is going to stick the best, it's going to have the largest net pulled down, and it's going to be most difficult to break or flatten this surface.